Hi everybody and welcome to the Chapter 9 summary. As you can see, I've upgraded the technology over here. So Chapter 9 is on free convection, which is when convection happens freely without any forced velocity in the fluid. As you remember, all the examples we went over in Chapter 8 specified a fluid velocity, so we were working with forced convection. In free convection, the buoyancy forces create currents in which there is small but naturally occurring velocity, leading to convective heat transfer happening. Imagine that you insert a flat vertical plate in a pool of stationary fluid. The temperature of the plate will slowly heat up or cool down the fluid parcels, causing them to change density and thus creating buoyancy. To simplify the scenario a little more and make it easier to formulate equations, let's assume that the fluid is incompressible. Technically, an incompressible fluid means that its density cannot change, but that is a critical factor in creating buoyancy. And so for that reason, we will assume incompressibility, but with the caveat that we allow the density to change only in the buoyant force. For this process, the momentum equation in the x direction can be written as u times du dx plus v times du dy is equal to negative 1 over rho times dp infinity dx minus g plus nu times the second derivative of du dy. In the case where density variations are due only to temperature variations, as is the case for this fluid with the vertical plate, we can define the property called the volumetric fluid expansion coefficient beta. And beta is equal to negative 1 over the density times the gradient of density with respect to temperature, and the subscript p means that this is considered at a constant pressure. The rest of this chapter defines Nusselt numbers for various geometries. Before covering those, I need to mention the Grashof number, which is another dimensionless group. The Grashof number is analogous to the Reynolds number squared when we take the following velocity. For this reason, the Grashof number plays the same role in free convection as the Reynolds number in forced convection. As with the previous chapters, the first step to solving a problem is determining if flow is laminar or turbulent. Surprisingly, it is possible to have turbulence with free convection. Instead of using the Reynolds number to determine the critical point, we define the Rayleigh number, which is another dimensionless value. The Rayleigh number is the product of the Grashof and Prandtl numbers, and if it is less than 10 to the 9th, the flow is laminar, but if it is greater than 10 to the 9th, then the flow is considered turbulent. For laminar free convection over a flat plate, the following Nusselt number correlation can be used. Nusselt number is equal to Grashof number divided by 4 to the power of 1/4 times g of Prandtl number, where the g of Prandtl number is equal to the following equation on the right. The average Nusselt number correlation is the following. Let's look at the correlations for external flow over a vertical plate. The following correlation can be used for all Rayleigh values, meaning it is appropriate to use for both laminar and turbulent flows. However, it has been found experimentally that it is not an amazing approximation for laminar flow, and so the following equation is generally preferable to use for laminar flow. These two correlations have been obtained for isothermal plates, meaning when Ts is constant. In the case of constant surface heat flux, the best result will be given if the Rayleigh and Nusselt numbers are calculated in terms of the temperature difference at the midpoint of the plate. So you can use the same equations, except calculate all the values at the halfway point. For flow over horizontal plates, there are various equations that depend on the location of the fluid and the temperature of the plate relative to that of the fluid. If there is flow on the upper surface of a hot plate, or if the flow is on the lower surface of a cold plate, then there are two Nusselt number correlations that are appropriate to use. The first one is that the average Nusselt number is equal to 0.54 times the Rayleigh number to the power of 1/4. The second correlation is that the average Nusselt number is equal to 0.15 times the Rayleigh number to the power of 1/3, and it has slightly different bounds for when it is appropriate to be used. Conversely, if there is flow on the lower surface of a hot plate or on the upper surface of a cold plate, then the Nusselt correlation to be used is that the average Nusselt is equal to 0.52 times the Rayleigh number to the power of 1/5. If instead of having a flat plate, we have a cylinder that is aligned horizontally, then we have Nusselt number is equal to 0.60 plus the ratio of 0.387 times Rayleigh number to the power of 1/6 divided by 1 plus 0.559 divided by Prandtl number to the power of 9/16, and then the whole denominator is raised to the power of 8 divided by 27, and then the entire thing is squared. The last geometry for external flow that we will look at is the sphere, which has the following Nusselt correlation. Before talking about internal flow, we should talk about the intermediate case between external and internal, which is a flow being sandwiched between two parallel plates. The plates do not have to be vertical or flat, they could be at an angle. If the two parallel plates are vertical, there are specific simplified correlations that can be used. In this equation, S is the distance between the two plates, and Ra sub S is the Rayleigh number evaluated at x equals S. This equation can be reduced further within the fully developed region, which happens when S over L approaches 0. So for that case, we can use the Nusselt number is equal to Rayleigh number at S times S over L divided by 24. And note that in the chapter, there are many more correlations for fully developed flow, and they depend on the boundary conditions on the plates, meaning if they are isothermal or if they have constant heat flux or a combination of the two. I won't go over these here for the sake of brevity. If the plates are inclined, then the Nusselt number is equal to 0.645 times the Rayleigh number times S over L to the power of 1/4. And here all the properties are evaluated at an average T, which is the average between Ts and T infinity. For fluid inside closures, we will consider three different geometries for the closures: rectangular cavities, concentric cylinders, and concentric spheres. A rectangular cavity is a box that has a fluid inside it. The box could be vertical, horizontal, or at an angle. For a horizontal cavity heated from below, we have the following Nusselt correlation. For this equation, all the properties are evaluated at the average T, which is the average between T1 and T2. For a rectangular cavity that is vertically aligned, there are many Nusselt number correlations, and I will put them all on the screen now. Let's talk about concentric cylinders. The heat transfer rate in units of watts for flow between two concentric cylinders is Q is equal to 2 pi L times Kf times Ti minus T naught divided by ln Rho minus Ri. The subscripts I refer to the inner cylinder and the subscripts O refer to the outer cylinder. Kf is the effective thermal conductivity and can be found through the following equation. Here, the subscript c means that the Rayleigh number must be evaluated at the critical length L sub c, which is equal to the following. The last internal geometry we will look at is for concentric spheres. The equations for concentric spheres are similar to those for concentric cylinders. We have a Q equation in terms of K effective, and then K effective can be written as an equation in terms of the Prandtl number and the Reynolds number evaluated at S. And so then you can find Ls with the following equation at the bottom. Take a look at the following problem. This question is about convection as well as radiation, so you can start mentally preparing for the near future when the class will focus on radiation. The first step to solving the problem is determining the appropriate geometry. We're given the dimensions and constant temperature of the oven door and are asked how much heat is lost to the room, meaning that we care about what is happening outside the oven. Thus, the door acts like a vertical wall. The heat lost to the room is found by the regular convection equation Q is equal to HA times the change in temperature, and so we must search for H. In order to do that, we must first calculate the Rayleigh number to see if our flow is laminar or turbulent. The values for beta, nu, and alpha must be resolved at the film temperature, which is the average between 22 and 32 degrees Celsius. After finding all of these properties from table 8.4 for air from the back of the book, you can then resolve the Rayleigh number, and you'll find that the Rayleigh number is equal to 1.142 times 10 to the 8th. We know that the temperature of the wall is constant, and so we would look at the two isothermal neutral correlations for vertical flat plates. And out of the two, the second one is said to be better for laminar flows, so we will use that one. Now, if we plug everything into the Nusselt number correlation, we will get that nu is equal to 53.82. And then we can solve for h. Now that we have h, we can plug it back into the main Q equation from above, and we will get that Q is equal to 9.9 watts. The loss by radiation is Q is equal to epsilon times A times sigma times Ts to the fourth minus T infinity to the fourth. And that is going to give us 21.4 watts. Remember that sigma is the Stefan-Boltzmann constant, and it is always equal to 5.67 times 10 to the negative 8th. And that the temperatures for radiation have to be resolved in Kelvin. So the final conclusion that we can make is that far more heat is lost by radiation than by free convection.